In the last lecture we have derived the Gershgorin theorem for finding bounds of eigenvalues. We call these bounds as Gershgorin circles. If the matrix is symmetric, then these Gershgorin circles reduce to real intervals. So, we can exactly tell the bounds or the end points in which the eigenvalues lie. Now, if we will now derive some numerical methods which gives the all the eigenvalues or all the eigenvectors, or if you need a particular eigenvalue, that particular eigenvalue and the corresponding eigenvector. Suppose that the matrix A is one of the three special forms, that if A is say a diagonal matrix. So, that is a diagonal matrix of this particular form, a diagonal matrix, or if A is a lower triangular matrix, we will have lower triangular matrix, or if A is an upper triangular matrix, in these three cases the eigenvalues are trivial, because all the eigenvalues are placed on the diagonal of this particular matrix. So, because we can write down the characteristic equation of this matrix as A minus lambda I determinant is equal to 0, it would immediately tell us that the eigenvalues are placed on the diagonal in all these three cases. Therefore, most of the numerical methods would attempt to reduce the given matrix using the similarity transformations to one of these forms, or some other forms that are also possible. Now, one particular method that we have is called the Jacobi method, for symmetric matrices. Now, the discovery of these methods actually started with from the problems that arose from the mathematical models from the physical problems. In most of the cases, the differential equations, ordinary or partial differential equations, the eigenvalue problems there had given rise to symmetric systems and having some special properties. Therefore, the original methods that were discovered were always for the symmetric matrices and with some special properties, which was later on when the problems were much more generalized, the symmetry was lost and you have general matrices. So, we have methods also for general matrices, but even today most of the practical problems in which we have and the mathematical models do give rise to symmetric systems. So, we know that we have earlier discussed some of the properties of symmetric matrices. One property is that all the eigenvalues are real. So, if A is symmetric, then eigenvalues are real. And secondly, we have mentioned that there exists a similarity matrix which reduces A to a diagonal form. Therefore, there exists a matrix which is non-singular, we will call it as S. There exists a matrix S such that S inverse A S is equal to D. D is our diagonal matrix. Therefore, all the eigenvalues are now located on the diagonal of this matrix D. Now, there is another property of the eigenvectors of a symmetric matrices. The eigenvectors of a symmetric matrices are all orthogonal. The eigenvectors of a symmetric matrix, that means corresponding to the eigenvalues that we have, they are orthogonal. Therefore, the matrix that we are constructing, we are talking of this non-singular matrix which is now reducing it to the diagonal form, is a matrix which is an orthogonal matrix. Therefore, this matrix that we are talking of here is an orthogonal matrix. That means S inverse is equal to S transpose. So, we will have here S inverse is equal to S transpose. Therefore, the similarity transformation that brings A to D now will be S inverse A S is same as S transpose A S, and that will be equal to D. This is the fundamental property of the eigenvalues of a symmetric matrix. Now, the Jacobi method attempts to reduce the matrix A to a diagonal form. So, that is the Jacobi method. Jacobi method reduces A to a diagonal form, reduces to a diagonal matrix. Now, how it reduces to a diagonal matrix is, we know that the applying a similarity transformation using an orthogonal matrix finally reduces A to D. Therefore, it attempts to find a series of similarity transformations in a plane which will be orthogonal rotations. Take a 2-dimensional coordinate system x y, then rotate it by an angle of theta. If I take the new coordinate system as x dash y dash, original system is x y, new system is x prime y prime, the angle of rotation is theta, then we know that the matrix of transformation that reduces is given by cos theta minus sin theta cos theta. Therefore, if you now take any point in the x y plane in this plane, then I can connect the coordinates of this point with respect to these two systems through this matrix, which is our rotational matrix. Now, you can see that this matrix is a orthogonal matrix, because I can try to find the inverse of this. If I take this as some S star, let me put as S star, then is S star inverse is equal to cos square theta plus sin square theta, that determinant is 1. Therefore, I have cosine theta over here minus sin theta here, sin theta here, and cos theta over here, and this is S star of transpose. Therefore, this is an orthogonal matrix, that means this is an orthogonal rotation. Therefore, the Jacobi method uses the orthogonal rotations in a plane to reduce the matrix to diagonal form. Therefore, we can say that we use orthogonal plane rotations to reduce A to D. Now, let us see how to do it. There it is to be done in 2 steps. Let us, what is the first step? Let us take the first step. Now, remember we are talking of symmetric matrix, therefore, we know Aij is equal to Aj. We shall use this property as we go along. We search first of all for the largest off diagonal element. So, that means look at the largest off diagonal element. So, the let us say among all the off diagonal elements, let us pick the largest in magnitude. So, let Aik be the largest in magnitude. So, if I take this matrix Aij, now it is symmetric, therefore, if this is the largest element in magnitude, this largest element in magnitude is also located here because of symmetry. Therefore, we have Aki is equal to Aik, and this will be the diagonal elements I have put it with a small dot. So, this is the location of these 4. Then what we do is we consider this 2 by 2 submatrix. Now, consider the 2 into 2 submatrix. This location is I, this is AIK, this is AKI, we can again put as AIK, and this is equal to AKK. Now, I consider this submatrix and reduce this element AIK to 0 by using the orthogonal rotation in the plane. Now, use orthogonal rotation. Let us put a some S1 star, so that we can use it. Use orthogonal rotation in a plane to get a 0 in IK, and it would mean KI locations. I think let us change, we shall use S1 for the rotation matrix. Let us call this as B1, I will call it as some B1. Now, let us take the orthogonal matrix in the 2 dimensional plane, which gives the required rotation as S1 star is equal to cos theta minus sin theta cos theta. Now, the problem is to find the value of theta such that the similarity transformation produces 0 in the IK and KI locations. So, I want to find the value of theta. Now, what is the similarity transformation? Similarity transformation is S1 inverse, here it is transpose A S star, and here we are applying it on B. S1 star transpose B1 S1 star. Now, this will be cos of theta, I am taking the transpose of this, minus sin of theta, this is sin of theta, this is cos of theta, that is the transpose of this matrix, multiply by B1 AII AIK AIK AKK into S1 star cos theta minus sin theta cos theta. Now, let us multiply it out. This is cos of theta sin theta minus sin theta cos theta. Now, this is AII cos theta plus AIK sin theta. This is AII cos theta plus AIK sin theta, and this element is minus AII sin theta plus AIK cos theta, and correspondingly this is AIK cos of theta plus AKK sin theta, and this is minus AIK sin theta plus AKK cos of theta. Now, since my effort is to determine theta such that the off diagonal element, that is location, this location is 0, I do not bother about what this element is, I shall be interested in what is this element and what is this element. Now, this element would be, I multiply the first row by the second column. So, I would have here minus AII cosine theta sin theta plus AIK cos square theta, I multiplied by cos theta this particular element, AII sin theta cos theta, AIK cos square theta. then I multiply this by sin theta. So, this will be minus a I k sin theta sin square theta, this is sin theta into sin theta, plus a k k sin theta cos theta. So, let us put a small bracket here. So, that we will have this. Now, let us write down this element. This element, because of symmetry, has to be the same, because we started with a symmetric matrix, therefore, this will also be symmetric part. Now, we can see that if I multiply it out, I will get here minus a I sin theta cos theta minus a I k sin square theta. I am multiplying this minus sin theta with this, and cos theta plus a I k cos square theta plus a k k sin theta cos theta. As I mentioned, because of symmetry, these two elements would be identically be the same. Now, the problem therefore is that I want to determine the theta such that we get location 0 in the locations of this I k and k I. Therefore, I will set this as 0 and determine theta. Therefore, that means set this is 0. So, let us simplify this. A I k, this is cos square theta minus sin square theta, that is cosine of 2 theta, plus these two combine a k k minus a I sin theta cos theta. Therefore, I will write it as half of sin 2 theta is equal to 0. So, let us now solve for theta. So, I can take this to the right hand side and write this as tan of 2 theta, tan of 2 theta is equal to 2 times a I k, and I will change the sign of this a I minus a k k. Or theta is equal to half tan inverse 2 times a I k by a I minus a k k. This value of theta will produce zeros in I k k I locations. So, this value of theta produces zeros in I k and k I locations. Now, tan 2 theta has got a number of solutions for this. More than one solution is available for this, but we would like to choose that value of theta which gives us the smallest rotation of all possible. So, that means we would like to take the value of theta lying between minus pi by 4 to plus pi by 4. So, take the smallest value of theta, in magnitude, smallest value of theta in magnitude, which lies in minus pi by 4 less than or equal to theta less than or equal to pi by 4. So, it has got actually 4 values it will have, of which we will have the smallest rotation possible, because we are going to do rotation after rotation, so that we bring the entire matrix to the diagonal matrix. So, we would like to choose the smallest rotation in the plane. That means, it essentially would imply that in a plane we are rotating the given system, again rotating the system, or maybe in the positive negative directions we are rotating the system a number of times, so that A is reduced to D. Now, you can see here some typical particular cases. If ai is equal to akk, the denominator is going to be 0, therefore, this will be infinity, therefore, tan infinity will be pi by 2. So, I will have the extreme values in those cases. So, I will have here, if ai is equal to akk and aik is positive, then this will give you plus infinity. If aik is positive, denominator is 0, it will give you plus infinity. Therefore, tan inverse plus infinity will be plus pi by 2. So, I will have theta is equal to pi by 4. Whereas if aii is equal to akk, but aik is negative, then this is a negative by 0, this is minus infinity, therefore tan inverse will be minus pi by 4. So, theta will be minus pi by 2 in by half, that is minus pi by 4. Therefore, if in any particular case we are fortunate to have the diagonal elements at that time to be equal, then they are going to cancel, then the rotation will be by an angle of pi by 4, and the matrix S1 star would look very nice, because in that case S1 star will be simply cos of pi by 4 1 by root 2, sin of pi by 4 1 by root 2, 1 by root 2, 1 by root 2. The rotational matrix looks very simple for our computational purposes. Now, when once the value of theta is determined, we would like to use the rotation on the whole matrix. Let us write A1 is equal to S1 inverse A S1, where our what is this S1 matrix will be? The S1 matrix will be all will be I except these 4 locations. So, the location of ik is here, diagonal element is here, ki is here, and your kk element is here. So, we will locate now cos theta here, we will locate minus sin theta here, sin theta here, cos theta here, and I in the remaining part. So, that means we are now absorbing these 4 elements to the correct locations, because when we started it, these are the 4 locations we have chosen, that is the submatrix A II, ik, ki, kk locations. Therefore, in these 4 locations these 4 values will go, otherwise the entire matrix will be simply I, and this will now be applied on the matrix A, and this would of course bring your 0 in the ki, ik locations. Now, if I perform this, that is your S1 transpose A S1. Now, this brings zeros, this brings zeros in the ik, ki locations. This brings zeros in the ik, ki. Now, one rotation is complete. So, the first rotation is complete. First rotation is complete. Now, repeat the procedure. Repeat the procedure. What we mean by repeat the procedure is that we shall again search for the last off diagonal element in A1, and now repeat the whole procedure that we have done. Find the value of new value of theta, which produces 0 in those off diagonal elements, and then complete the rotation like this. After a number of rotations, A goes to D. Then eigenvalues are located on the diagonal of D. On the diagonal of D. Now, before we just make a comment on the number of rotations that is required and what are the eigenvectors from the system, let us make a comment here, that is about the disadvantage of the Jacobi method. If that disadvantage was not there, then this Jacobi method would have been the best method, and we do not need any other numerical method. The disadvantage in this method is that 0 that is created once can be disturbed or may be disturbed in the later rotations. That means, if I produced a 0 in say location 9, 10 and 10, 9 location, and if I go to the further rotation, this 0 can be disturbed and it can become a non-zero quantity. That means, at a later stage we again have to make this number that has been produced here as a 0 again. That means the number of rotations will not be exact, we will not be able to predict what will be the number of rotations that is required. Therefore, we can only state how many minimum number of rotations that will be required for reducing A to D. Therefore, this is the main disadvantage. A 0 that is created may become non-zero in a later rotation. Therefore, a 0 that is created may become non-zero in a later rotation. Therefore, we can only say the minimum number of rotations Now, let us see what is the number of elements that we will have to bring them to 0. We are now on the diagonal. Now, because of symmetry, the Aij elements is equal to Aj elements. Therefore, I need to bring these n minus 1 elements to 0, then I have to bring n minus 2 elements to 0, and finally 1 element to 0. So, the number of elements that is to be made to be 0 odd, let us count from bottom, 1 plus 2 plus 3 so on n minus 1. So, this is the number of elements that are to be made as zeros. Therefore, the number of rotations thereby will be n minus 1 into n by 2. So, this will be the minimum number of rotations that will be required will be n minus 1 into n by 2. But of course, if you are doing the exact arithmetic by hand, that means do not convert theta into the decimal form, and if you are able to write exactly the values of theta, then it is possible for us to retain these zeros that is created. Now, let us find out what is the eigenvectors when once we know that yes, I need this many number of rotations and I can now find out all the eigenvalues, and then let us see what is the eigenvectors. Now, let us just repeat what we have done the first rotation. I will start from the middle of this line. We have S1 inverse A S1, this is the first rotation. Then I have applied here another similarity transformation S2 inverse S2, this is my second rotation, this is my second rotation, so on. I am now applying, we know that the minimum number of rotations is this, therefore, let us say we needed some R rotations. So, I can make this as R, I can make this as SR inverse, and this is finally our matrix BR, and that is your D. Therefore, this is the first rotation, the next rotation, and finally the rth rotation that we have needed to reduce the matrix A to the diagonal form D. This is how sequence of rotations looks like. Now, let us simplify this. This I can write, let us first of all write down the right hand side, this is S1 S2 SR. So, I will take this as S1 S2 SR. If you look at this left hand side, this is SR inverse SR minus 1 inverse S2 inverse S1 inverse, that is the inverse of this. This is your S1 S2 SR inverse. The inverse of this is nothing but this inverse, and this is, I will now call this as S inverse AS. Therefore, where our S is equal to S1 S2 so on SR. And this is the product of all rotation matrices that we have used. This is the product of all rotation matrices. Now, I have got the matrix, final matrix, product of all matrices. This is the matrix of eigenvectors, and this is the matrix of eigenvectors. Now we mentioned earlier, if you remember the earlier discussion, we mentioned that if a matrix A is reduced to a diagonal matrix, then there is 1-to-1 correspondence between the eigenvalues located on the diagonal of D and the columns of S. Therefore, when once I get the matrix of eigenvectors, then the first column will be the eigenvector corresponding to the first eigenvalue. Let us put this as lambda 1, lambda 2, so on lambda n, and let us write S is equal to column 1 vector, column 2 vector, column n vector. So, let us write S as the column vectors C1, C2, Cn as the n column vectors of S. Then Ci will be the eigenvector corresponding to lambda I. Then Ci is the eigenvector corresponding to lambda I. Therefore, for finding the eigenvector we do not have to do anything extra, except that we have to multiply these matrices S1, S2, Sr matrices and then take the columns as the corresponding eigenvectors, and they would almost be in the required form of normalized form also, and we will have the eigenvectors available for us automatically. Now, let us take a simple example on this. Now, I will take a very simple example which we will do by exact arithmetic, and we will also show that even though we said you need n minus 1 into n by 2 number of rotations, if you are if the matrix is such that it is you are doing the exact arithmetic, you may get it required form earlier than the number of rotations also. So, let us take this as a very simple trivial example. So, take the using the Jacobi method. Using the Jacobi method, find all the eigenvalues and the corresponding eigenvectors of, let us take A is 1, root 2, 2, 3, root 2, 2 root 2, 1. Now, the first of all I need to locate the largest off diagonal element. The largest element in magnitude is 2 here. So, we will have here as largest off diagonal element. Now, here they are all positive numbers, so we do not have to say magnitude, but otherwise we will have to take the in magnitude. Largest off diagonal element is equal to 2, and this is your A13 is equal to A31, A13 is equal to A31, and the corresponding diagonal elements are A11 is 1, A33 is equal to 1. So, with respect to this element I am now taking that sub matrix, that is your diagonal elements are 1 and 1 and this is 2. Now, I find theta, theta is equal to half tan inverse 2 times A13 by A11 minus A33, and this is half tan inverse of plus infinity. A11 is equal to A33 here and A13 is positive, therefore, we have plus infinity. Therefore, the value of theta is pi by 4. Now, I will write down the rotation matrix, first matrix S1. We said S1 will be I, matrix I, except the elements corresponding to this 4 elements. The 4 elements are this, this, this and this. Therefore, cos theta will come here, minus sin theta here, sin theta here and cos theta here. Therefore, our S1 will be cos of theta 1 upon root 2 0 minus 1 upon root 2 0 1 0 1 upon root 2 0 1 upon root 2. Therefore, this is the rotation matrix that we need. Now, we need A1. A1 is S1 inverse, that is S1 transpose A S1. So, let us write this 1 upon root 2 0 this is I am taking the transpose. So, this comes here, this is 1 upon root 2 0 1 0 1 upon root 2 1 upon root 2. The matrix A is 1 root 2 2 root 2 3 root 2 2 root 2 1. Then we have got S1, that is your 1 upon root 2 0 minus 1 upon root 2 0 1 0 1 upon root 2 1 upon root 2. Now, let us retain the matrix, this matrix as it is. Let us multiply these two matrices. So, I will have 1 into 1 upon root 2, that stays as it is, this is 0, this is 2 times 2 by root 2. So, that will be 3 divided by root 2. Then 1 into 0 root 2 2 into 0. So, I will have simply root 2 here. Then minus 1 upon root 2, this is 0, this is plus 2 upon root 2. So, I will have here 1 upon root 2 here. And second row I take, this is 1 upon root 2 into root 2, that is 1 0, this is 1, that is equal to 2. Now, the middle row is 0 1 0. So, this multiplies 3. Then this is minus 1 0 plus 1. So, we will have 0. Then 2 by root 2 0 1 by root 2, that is 3 by root 2. Then this is the middle element, that is root 2. This is minus 2 by root 2 and plus 1 upon root 2. So, we will have here minus 1 upon root 2. Now, let us multiply the whole thing. Now, I am multiplying this row with this column. So, I will have here 3 by 2 into 0 plus 3 by 2. So, I will have 3 by 2 plus 3 by 2, that is 3. Then 1 upon root 2 into root 2, that is 1, this is 0, this is 1, that gives me 2. 1 upon root 2 1 upon root 2, that is 1 by 2 0 minus 1 by 2. So, that gives me 0. Then middle row 0 1 0, therefore, it will the middle row comes at 2 0 2 3 0, this middle row and this one. So, it will have simply this, and the third row, this is minus 3 by 2 0 plus 3 by 2. So, I have a 0 here, this is minus 1, this is 0, this is plus 1. So, I have a 0 here. Then this is minus 1 by 2 0 minus 1 by 2, minus 1 by 2 minus 1 by 2, that gives me minus 1. Now, we in one rotation we started with trying to get the 0 in these two location, but we now got an extra 0 also here, these two also have become 0 now. Now, I need to make only one more element as 0. I know the largest off diagonal element is 2. So, that is my step 2. Step 2 is now I will take the largest off diagonal elements, largest off diagonal element is equal to A12 location, that is 2 and A21. Now, the corresponding diagonal elements are A11 and A22. So, the corresponding diagonal elements are A11 is 3 and A22 is equal to 3. I again determine my value of theta from here. Theta will be equal to half tan inverse 2 times A12 by A11 minus A22. Again this is plus infinity, A12 is positive, therefore this is again plus infinity, therefore I have the value as pi by 4 again. Now the values of cos theta, sin theta would lie in these 4 locations. We are making A12 location as 0, therefore cos theta will be here, minus sin theta and cos theta will be located here. Therefore I can write down my matrix S2 will be cos theta minus sin theta, cos theta, remaining is all I. So remaining is all I. Now we perform our rotation with respect to this new matrix. Therefore, S2 transpose A1 S2. Therefore, let us write it as 1 upon root 2 minus 1 upon root 2 0, 1 upon root 2 1 upon root 2 0 0 0 1, that is our inverse, and A1 is 3 2 0 2 3 0 0 0 minus 1, and S2 is 1 upon root 2 minus 1 upon root 2 0, 1 upon root 2 1 upon root 2 0 0 0 1. Now let us multiply it out this matrix again. Therefore this gives us 3 by root 2 plus 2 by root 2, that is 5 by root 2, 5 by root 2. This is minus 3 by root 2 plus 2 by root 2, that is minus 1 upon root 2. This is 0, this is 0, this is 0. So I have a 0 here. Again 2 into 1 upon root 2 plus 3 by root 2, that is again 5 by root 2. This is minus 2 by root 2 and this is plus 3 by root 2. So I will have plus 1 upon root 2, and this is again 0. 0 0 minus 1, therefore it will be 0 0 minus 1. Now let us write it here itself. Now I am multiplying this row and this column. This is 5 by 2, this is 5 by 2. So I will have here 5. This is minus 1 by 2, this is plus 1 by 2. So I have a 0 here, and this is again 0. Now second row, these are opposite signs, they are equal opposite sign. So I will again produce a 0 here. This is plus 1 by 2 plus 1 by 2. So that will give me 1. This is 0 0 0 minus 1. Therefore we have now finally produced the diagonal matrix. Therefore here we can immediately write down that our eigenvalues are 5 1 and minus 1. These are the eigenvalues of our system. Now I need eigenvectors. We have S is equal to S1 S2, I need to find this product. Now if you just go back and write down what is our S1 from here, these are the 4 locations in which these are 1 upon root 2 was located. So let us write this as 1 upon root 2 0 minus 1 upon root 2 0 1 0 1 upon root 2 0 1 upon root 2. So this was our S1. Now we can write down the value of S2 that we have obtained earlier as, this is 1 upon root 2 minus 1 upon root 2 0 1 upon root 2 1 upon root 2 0 0 1. Now multiply it out, I will have this as 1 by 2 and this is 0, this is 0. So, I will have here 1 by 2, this is minus 1 by 2 because this is 0 multiplied, this is also 0, this one, and this is minus 1 upon root 2, this row and last column. So, the middle row it will repeat again. So, 1 upon root 2, 1 upon root 2, 0. The last row gives us 1 upon 2, these are zeros. So, this is 1 upon 2, this is minus 1 upon 2, 0 0. So, minus 1 upon 2 and lastly 1 upon root 2. We said that the correspondence of the eigenvalues and eigenvectors is the first eigenvalue first column, second eigenvalue second column, or the corresponding eigenvectors. Therefore, lambda is equal to 5 and let us call V1 as our eigenvector, that is your half 1 upon root 2 2 as the eigenvector. Lambda second eigenvalue was 1, therefore, the second column C2 is equal to minus 1 upon 2 1 upon root 2 minus 1 upon root 2 as the eigenvector, and the third eigenvalue minus 1 is the third column here, V3 is minus 1 upon root 2 0 1 upon root 2. Therefore, these are the corresponding eigenvectors and the eigenvalues are located on the diagonal of this, and we have this particular this one. Now, in practice what really happens is, when you are finding the value of theta on the computer, the value of theta here we have made the exact arithmetic, cos theta is pi by 4, we retained as pi by 4, cos theta is 1 upon root 2, we retained it. But when once you write it in the format in the decimal numbers and go to the computer, some of these numbers get disturbed. Therefore, the locations that were zeros will be destroyed and you will have non-zero numbers, and those non-zero numbers have again to be made as zeros. Therefore, the number of rotations thereby increases. Even if I disturb the elements of the matrix slightly and ask you to do it, you will find that you may need about half a dozen iterations or so to reduce into this particular form to a given accuracy, because the computer is going to stop when off diagonal elements are of accuracy of say 10 to the power minus 6 or minus 7 or so. So, the number of rotations that will be required depend on the accuracy in the particular problem, and thereby the amount of time also, computer time also depends on that. Therefore, in advance we will not be able to say that the Jacobi method will take this many rotations or this much computed time to solve this particular problem, but it can definitely give us the solution. If you can give the sufficient amount of time for it, yes, Jacobi method will always give us the solution, all the eigenvalues and the eigenvectors. Okay, we will stop for today.